Okay, we're back. Last time out, we talked about electric potential, and that was kind of the bridge between electrostatics and what we're going to go into now, which is electric circuits. So what we're going to talk about today is electric current. Okay, electric current. Now, why have we learned all this stuff about electricity? Okay, it's great to know that certain objects have charges and they are attracted to each other and they cause electric fields to be created. But what's the real point? Okay. The main reason we study electric charges is because we can use electric charges, we can manipulate them and control them to provide energy where it is needed. Okay, that's the whole reason we're learning this. We're really learning about how to provide energy where it's needed. In order to effectively provide this energy, we take these charges that have certain amounts of energy and we channel them and we basically make them move through certain objects. And when we take charges and we move them in a certain way, in an orderly fashion, we say that we are creating a current. And we channel this current through conductors. Remember, conductors are any material that allows objects to very easily, allows charges to easily move. And by charges, again, what are we really talking about? We're talking about electrons. So, electric current, the definition: movement of charges past a point. Okay? Current is just like you're counting how many charges are going past a point in a certain amount of time. And there is an equation for this, and I do have to grab my reference tables. They're hidden from me at this moment. Are these them? Yes. Okay. So, there is an equation for current. Let me flip to the electricity page. That's page 4 if you haven't noticed. Here are the equations we've studied so far. Fe equals kq1q2 over r squared, E equals Fe over q, and V equals W over q. So that's 3 of them. We're actually going to hit 3 more in this series of video lessons, okay? First one we're going to start off with is this right here. I equals delta Q times T. I being current, okay? I is the symbol for current. You're just going to have to get used to that. Q being charge. There's a delta there because we're moving the charges around, so it's not really change in charge. What they really mean is how many charges are moving past a certain point divided by in some sort of time period. Okay, so we have, let's set that over there. I equals delta Q times T, where delta Q is how much charge passes a point. And this is in coulombs. So if we're given elementary charges, we do have to convert to coulombs. Okay? The units of this, if you look at the right-hand side, charge has units of coulombs divided by, and then T is units of seconds. This is known as an amp, or an ampere, with a little accent grave there. And let's see, we'll just pluralize it. The symbol is A. Okay, the symbol is A. And for our purposes, this will be a scalar. Yes, we do, I guess we do, that's kind of a vector. We do have to know what direction the current is flowing, but that's not really all that important because we could very easily change that around. Okay, if you're looking for an analogy for current, imagine, let's say, cars on a highway. If you've ever seen pictures of Los Angeles during rush hour, there's cars bumper to bumper for miles and miles and they can't really get through, and they're moving very, very slowly. That's kind of like what current is. If you were to stand to the side and count how many cars are going past you maybe per minute, that's kind of like the flow rate or the current of cars going past. My personal favorite analogy for around here is to liken it to the Boilermaker. If you were to stand at the beginning of the Boilermaker when all 14,000 of us are at the starting line and we're all kind of making our way past, and you were able to count how many people are going past you, let's say per second, you're finding essentially a current of people, number of people per second. Electric current is just a number of charges flowing per second. All right, let's get to an example of using this equation. If 5 times 10 to the 18th electrons pass by a certain point in a wire in 1 second, what is the current? Well, remember, we do need to have this, we're looking for the current, we have time, 1 second, we do have the charge, but we need it to be in coulombs. So we need to convert this. Right now, we just know how many electrons there are, which means we know how many elementary charges there are. So 5 times 10 to the 18th E. We know that from the reference tables, 1 elementary charge is equal to 1.6 times 10 to the negative 19th C. So we convert. And we end up with 0.8 coulombs of charge. From there, it's very simple. 0.8 coulombs divided by 1 second. That must mean the current is 0.8 amps. Okay, so simple equation. Notice that even though it was electrons, so they're negative, I didn't say negative current. Okay, this is another case where even if the charge that's flowing is negative, we're just going to leave that negative off. Okay, we're going to ignore it. So, the equation is fairly, oh my gosh, I didn't even write the equation. There we go. Okay, so even though this is a fairly simple equation, just please remember there are a couple things. The charge, you're always just going to keep the charge positive, even if it's negatives, negative charge is flowing, and make sure that the charge is in coulombs, okay? Most circuits make use of wires and other electrical devices to deliver energy. We're not just flinging electrons out wherever they have to go. We guide them through the use of wires. Wires are just conductors. Wires are made of metal, so what happens is they actually have plenty of extra electrons that can be used in a circuit. If you remember from chemistry last year, you probably talked very briefly about how metals have this thing called the sea of electrons. Metals hold on to their electrons very, very loosely. So it's very easy to move electrons around in a metal. And what happens is if you set up an electric field, which will cause a potential difference, remember that's what we talked about last time, electric potential difference. If that causes an electric potential difference between 2 different points, then what will happen is you will influence those electrons to kind of hop along the atoms in the metal and move from one point to another. Okay, that's why we use wires, because wires have plenty of extra electrons. If we set up an electric field and induce what's called a potential difference between 2 different points, we can move those electrons through the wire from one place to another in an orderly fashion. Let's talk a little bit about how a circuit works. That's the general gist of it. But any circuit really needs 3 things, okay, in order to operate correctly. Circuits need a power or voltage source. They need what I like to call an energy consumer. And they need a way to link those two, which is wires. Every single circuit, every working circuit has those things. A power or voltage source, an energy consumer, and wires. So someplace that stores energy, someplace that needs energy to get to it so we can do whatever it is we're trying to do with the circuit, and a way for the energy to get there, wires. And again, how the energy is getting there is it's being carried by these charges. So let's talk a little bit about what all these things are. A power or a voltage source. We go back to this page. We're going to learn the circuit symbols because we're going to be drawing a lot of circuits in this class, in this portion of the class. So a power or voltage source, somewhere that stores energy that we want to get somewhere else. The symbols for those 2 things are the first 2 in here. We have cells and we have batteries, okay? A battery is just a whole bunch of cells put together. So usually we just use the symbol for battery. But both of those refer to somewhere where energy is currently stored that we want to eventually bring somewhere else. So we have a cell. You should understand, you should know what these symbols are. And again, they are just listed right for you in the reference table. Okay. There's a cell, and there's a battery. You can see my symbols are the same. Okay, get used to these symbols. Now, each of these stores energy. A cell and a battery, that's what they do. And the way that this works is between the 2 different ends of the battery, between, and you guys remember what the ends of a battery are called? We haven't discussed in this class, but you probably know it from like elementary school. We have a positive terminal and a negative terminal. So between the positive and negative terminals, there is a potential difference. Again, potential is a thing that you can measure. There's a difference in electric potential between this end and this end, okay? Between this end and this end, there's a potential difference, which means that essentially there's, what it really boils down to is it's like there's an energy difference. It's not exactly the same thing, but they're related, okay? And we know that charges, positive charges like to move from high energy to low energy, or all charges like to move from high energy to low energy. If they're in a state of high potential energy, they will try to move to a state of lower potential energy. And that energy that they lose, the potential energy they lose, gets turned into kinetic energy or some other type of energy. Okay? So we have positive and negative. Okay, so what happens is the current will flow out of the positive terminal. And at this point, it has lots of energy. Flows into our energy consumer, okay? Energy consumer is something that uses the energy for some purpose. Or in other words, there is what we call a decrease in potential. Or what it really means is a decrease in the energy carried by the charges. Here are some examples of energy consumers. Here are the ones that we will focus on. It's these three right down here: resistor, variable resistor, and lamp. All of these use energy. They take energy from those charges and they use it for some purpose. What a resistor really does, and we'll play with resistors virtually, a resistor is something that dissipates energy in the form of heat. Okay? It causes, as current runs through it, it will actually warm up and it gives off energy that way. A variable resistor is the same thing as a resistor. It's just got this little arrow symbol on it, and it sounds exactly like it is. It's a resistor that you can change the resistance of. Most of these resistors, most resistors that you would see in real life they're set in their value of how much energy they give off, what the resistance is. A variable resistor, you can play with the resistance and turn it up or down. And we'll talk about what resistance means in a little bit. And the last one is a lamp. Now this gives off heat energy as well, but as you probably know from, being a human, having experience, a lamp also gives off energy in the form of light. So all three of these give off energy somehow. So current comes from the power source, goes through the wires, goes to the energy consumer. The charges give up their energy. It gets turned into some other form. And then the current doesn't just stop. The charges don't just stop. They eventually flow back to the other end of the battery. At this point, they have low energy because they've given it up. Every single circuit essentially functions like this. There is something that should be a little confusing to you. Maybe you picked up on it, maybe you haven't, okay? I said this was the positive terminal, and this was the negative terminal down here. Now, we have always talked about what type of charge can flow. We always say electrons can move around. So this should be a little confusing because you should be like, well, wait, if this is the positive terminal, and we know that opposites attract, and electrons are negative, and they're the ones that are flowing, why would the electrons go away from the positive terminal? And that's a really good question. And the answer is, they don't. In reality, what happens is electrons are repelled away from the negative terminal and go towards the positive terminal. However, we're going to talk about something in this class. We are always going to assume that the flow of charges, that positive charges are actually flowing. This is called conventional currents. And there's a lot of history behind this. Back before we knew what electrons and protons were, we weren't sure which type of charge actually flowed. So what we did was we assumed that it was the positive charges that flowed in circuits like this. It turns out that's not the case. So what we assume in thinking about okay, let me back up. What actually happens is electrons are repelled from the negative terminal, go towards the positive terminal. What we assume happens, which ends up doing the exact same for all our calculations, is saying that positive charges are repelled from the positive terminal and go to the negative terminal. It's kind of like a double negative. Instead of saying for this particular circuit I've drawn right here that negative charges flow counterclockwise, we say positive charges flow clockwise. It ends up giving us the exact same thing. So when I talk about current, I will always talk about it as if we have positive charges flowing from the positive terminal to the negative terminal. It's up to you to remember that in reality what happens is we have negative charges flowing the opposite way. Take my word for it, it ends up giving us the exact same answers. We can analyze it the exact same way. It's kind of like a double negative in English, okay? When we come back, I will show you all of this stuff on a computer on a little simulation site we'll be using, and we'll continue to talk about electric current and circuits and how to set them up.